and finite intersections of families of sets in T are again in T. Meaning, take a family of sets. I'm not writing it out in great detail. It will look like take a family of sets xi, I belonging to I, xi belong to T, implies union xi belongs to T. And finite intersection will be if moreover I is finite, then intersection also belongs to T. And it is here that I might like to take I to be empty and declare the empty intersection to be all of X, but you may be unhappy with this. In that case, let me add it explicitly that X belongs to T, or some people right here add empty belongs to T and X belongs to T. Okay. Okay, so these are what is called T. Not important how your number is. Have I missed out anything? Is this the definition of a topological space? Of course, modulo the fact I allow it to be empty. Is this the definition of topological space? Somebody just say yes or no.
Yes, yes.
Yes, very good. Given my refusal to open books, I can sometimes make mistakes. So you guys have to be alert. Because after reading the first line of Simmons, which said that take a non-empty set, I close the book. Therefore, now what follows is not directly, from Simmons, but it is standard topology. Okay, so this is what is a topology. And then xt, and I should say here such a T is called a topology on X. And xt is called a topological space. Okay, so now these are the objects of top. The objects of the category top are all topological spaces. What are the arrows? Arrows. F from xt to x prime t prime are all continuous maps. From x to x prime. And what does continuous mean? So if you recall, for continuity in terms of metric spaces, one of the equivalent formulations is inverse image of an open set is an open set. So that becomes the definition. So this means if U prime belongs to T prime, then F inverse of U prime should belong to T. So this is what is a continuous map from one topological space to another. Now, usual notational shortcut, we will, as usual, write xt. simply as t, simply as x. So perhaps writing it simply as t might. Anyway, all right. So when t is understood, when t is understood, okay, this is as usual. This is a notational convention as usual. So with this definition of arrows, now let's come back here. So I have to give you some examples of empty spaces, of topological spaces. So the empty space itself is a topological space for us. So just to make sure you understand the empty topological space, let me ask. So suppose I take X to be empty, then what is T? There's only one choice for T. Is T also empty?
No.
No. So what is T?
Singleton containing empty set.
Okay. So whosoever said this, singleton containing empty set, who said that? Who answered this?
Shubham Jaiswal.
Name?
Shubham Jaiswal.
Okay. So Shubham, you are right. And so if that is the empty set, X is the empty set, then at least empty set has to be open, all of it has to be open, and both of those are the empty sets. So the empty set has to belong to T, and because empty set has to belong to T, and there is no other possible subset anyway, so this is phi. Okay, so this is the empty topological space. This is the empty topological space. Now let X be anything, X any set. Then there are always some extreme topologies on it. One of them is called discrete topology. In that, the simple description of T is the power set, the set of all subsets. Of X. And in discrete, for here T only has two elements. One is phi and one is X, and those two may be one and the same in case X is itself an empty set. So as you all know, open sets in X mean elements of T. Okay, so here I said, so I could have said this, that inverse image of an open set is open. That is the meaning of a map being continuous. So I can ask you all kinds of usual questions. What is the identity map from X discrete to X indiscrete continuous? Yes or no? So let me call this topology indiscrete.
Yes.
Yes. So identity from X discrete to X, this is the identity on X. So clearly it's a very bad notation because that's not the identity of your category. Okay. A very bad notation. Anyway, so that map from to X indiscrete, in which X maps to X, is continuous. This is why when you keep changing topology, calling, and now let's take the other one, X indiscrete. Again, take the map which is identity on the underlying points. X goes to X. How about this one? Is this continuous?
No.
Need not be. Okay. Need not be. Give me an example where this map is also continuous.
If X is empty.
Any other example?
If
X is singleton.
Excellent. So these are examples and these are the only examples. Otherwise, this can't be. Okay. Because then they are one and the same. That's why. So an isomorphism in top, in the category top, has a special name. What's the name?
Homeomorphism.
Homeomorphism. You see, notions such as homeomorphism were invented before categories were invented. Therefore, only after categories were invented, you realize that, oh, a homeomorphism is just an arrow in top which is invertible. So X is a topological space and Y, F, so this is an arrow in top. This is an object of top. This is an arrow in top. So this belongs to should not be taken literally. So I am wiping it out to avoid any misunderstanding. So this is an arrow in top. This is also an object in top. So F is an isomorphism, which means there exists another arrow from Y to X. So is that, let's call it G. So that GOF is the identity arrow of the topological space X, and FOG is the identity arrow of the topological space Y. You see, this definition of isomorphism made no reference to what that category was. These may be groups and group homomorphisms. These may be rings and ring homomorphisms. These may be topological spaces and continuous maps. These may be metric spaces, and one of those things, say non-expanding map. Whatever it is, isomorphism in that respective category simply means an invertible arrow, which will have respective meaning in all those categories. So when you are going to argue with arrows and isomorphisms, a categorical argument will work in each one of those examples. You understand the power of categorical abstract thinking, because then that allows you to forget a whole lot of detail and give general arguments which are very valid. You don't have to open the bonnet of the car every time. Okay? In all those cars, pressing the accelerator speeds it up, and turning the steering wheel to the right makes the car go to the right. And you don't have to look inside what is the mechanism, because all of them satisfy certain basic properties. Those are the definitions of category. And after that, you are free to drive the car without all the time bothering about this gear has now engaged with that, and now this hydraulic has happened, blah, blah, blah. Okay? That's the power of abstraction. Okay. So let's go back to what I want to tell you. So I have told you that this is a category, but you have to check it is a category. So to check it is a category, what do I have to check? If this is continuous, and if this is continuous, are continuous, imply GOF is continuous. So this is the composition and obviously the way it is defined, if I have four things, X, Y,
Sir.
Yeah.
Sir, for the checking of identity, like if we want to impose a category, so we need a identity, right?
Right, that's coming.
So
That's the next thing. Yeah, but why are you in a hurry?
Yeah, okay. Next.
So I first want to show that what should composition satisfy? F, G, H, G of F. On the other hand, here is this, which is HOG. So I should have that H composite GOF equal to HOG composite F, associative. The composition should have two properties. It should be associative and there should be an identity. So the identity map of X, remember the topology is the same on both sides. Otherwise, the identity map need not be continuous, as you know from our indiscrete, discrete, whatever examples. Okay. X maps to X is continuous. So it is an arrow in top and it is left as well as right identity for composition. That obviously it is. So both these properties, that this is associative and this is left and right identity for composition, are obvious because all that you are doing is defining a map on underlying sets where you know these properties. But what you need to check is these maps are indeed continuous. The composite so defined or the identity so defined is indeed continuous. So after all this work is done, we have set up the category of topological spaces. So the category top of topological spaces and continuous maps has now been set up, and I have given you some examples. The final example is topological space associated to a metric space. Okay. So given a metric space, I can define T to be the collection of all open sets in that metric space, meaning any point of that set has an open ball around it in that set. Empty set satisfies it vacuously. These I declare to be my elements of T. And now such a T is a topology that is called the metric topology on the metric space. So any metric space has a metric topology. Okay. And then a continuous map of metric spaces in the sense that it preserves limits of sequences or whatever epsilon delta definition that you have been introduced to. Those things, under them, inverse image of open sets is open. Conversely, if I have map between metric spaces such that the inverse image of every open set is open, then such a map satisfies the epsilon delta definition or preservation of limits definition of continuity of metric spaces. So the two notions of continuity coincide for metric spaces. I think if the tutors are able to hear me, keep that as an exercise in the tutorial, that the students should be asked to show that indeed this is a topological space. The metric topology indeed gives a topological space, and continuity in the sense of metric between two metric spaces is the same as continuity in the sense of topological spaces between the resulting topological spaces. Yeah, Saibal, is the exercise clear?
Okay. Yeah, okay, sir. Okay, sir.
Yes. So this exercise should be included. Perhaps you already included in your last week. Okay. So now you may ask, so what have we achieved? Well, we already had metric spaces and continuous maps. So there are two things which are achieved. One thing is, let me change the color and emphasize these points. For many aspects of metric spaces, X, D, all that matters and their maps all that matters is the associated topological space. X, and perhaps I should call it TD, the topology made from the metric. And so you don't have to remember the metric, which is why people have been giving you exercises such as, you're asked to show that if I have this R2, and then you have different metrics, and they give you these different open sets, etc., 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 and they are all quote-unquote equivalent. So unless you are a tailor or say a differential geometer or many other very important things which require you to measure the precise distance and therefore depends what formula you use. Otherwise, it doesn't matter. It's rubber sheet geometry. But there is another reason. But there are topological spaces. There are important topological spaces whose topology T is not of the form, so there are topological spaces X whose topology T not of the form topology coming from D, where D is a metric. So this xt does not come from any xt. So you have to study them as topological spaces. So here are the two things. One is lots of things about metric spaces are really about topological spaces. And so it's much easier arguing with topological spaces. You don't have to all the time remember the metric. And the second thing is there are lots of topological spaces which don't come from metric spaces. So now we shift from metric spaces to topological spaces. At this point, you may wonder what are these important examples which don't come from metric. So for example, in all of algebraic geometry, you study so-called Zhaisky topology, and that doesn't come from metric except in exceptional cases. And that topology is very important for the study of algebraic geometry. There are plenty of such examples. Okay. So let's go back, see whether I have achieved the primary aim. Okay. Aim number 1 of this lecture was to introduce to you the category of topological spaces. Now that I have introduced this category, let us start studying this category a bit more. So let me start my usual questions. Does top have an initial object? What's the answer?
Indiscrete.
Well, in the topological category, you have to give me an object of the category, which means you have to give me a topological space, and you have to say this topological space is an initial object. So what topological space is an initial object? Or you want to say that any indiscrete space is an initial object?
Singleton certified.
Empty set and
What is a topological space? Is that given any other topological space, this topological space has a unique continuous map to it.
so singleton set. And
Yeah, who is saying? Who is answering? Anuj?
yes, sir.
Anuj, what's your answer?
Sir, singleton sets.
Singleton set. Well, no, wrong.
Hello.
Yeah.
Sir, singleton certified.
I'm thinking that discrete space on X will be the initial point.
No. And what is X? You have to give me an example, not just X.
Hello,
Okay,
sir.
so very simple. It has an initial object, and that is empty. Empty space is the initial object of topological spaces. Given any topological space, the empty space has a unique map to it. Yeah? Empty set was the initial set, no? Given any other set, empty set had a unique map to it. That was lecture number 1. You know, I'm beginning to see the point of Simmons. I'm beginning to see the point of Simmons that his book will not sell. You know, students have great difficulty with the empty set. And that's amazing for your generation who were introduced to sets from your school era. So if no publisher will perhaps like a book in which empty set is mentioned, because then the book is not sold. What's happening, guys? Do you understand now that empty set has a unique map to any other set? Yeah.
Yes,
Sir.
yes.
Yes. Okay. And is that map continuous? What's the inverse image of any?
Inverse image of any open set is an empty set, and empty
Empty,
set
and
is
that is open in the empty space. Yeah.
yes.
We just now defined the empty topology. There it was.
Hello,
In the
sir.
empty topology, the only open set is the empty set. Now, if you take any map X and take from empty set to it, the only map, inverse image of any set, there is the empty set, which is open. Yeah, so that is open. Now, I think you guys need to meditate on this, because this is really elementary. It don't require any knowledge, it just requires some clear thinking.
Hello, sir. Am I audible?
Yeah.
Sir, I had a question, and the
Yes,
question
please.
is that in the category of topological space, an empty object, that is an empty space.
Not empty object, empty set, empty space.
Empty set,
Empty space, call it space now because we are in topological spaces.
Yes,
Empty space.
empty space.
See, what is the empty space? Let's again show you what is the empty space. The empty space, because we have suppressed the name of T, you see. So by that we mean phi, comma, phi. This is X and this is T. X is empty and the topology is this. But you remember our convention, we write the name only of X and suppress the name of T. So this is that. Okay, so now continue with your question. So what are you saying?
So if I include such a space in my category, then the advantage of including this is that every function from this space to
Who
any
is
other.
speaking, by the way? Please identify yourself.
Hello?
Yeah, what's your name?
Roshni, sir.
Roshni. So Roshni, what's your problem? You are talking philosophy or you have understood what I'm telling you?
Sir, I'm clearly understood what you are telling.
Have you understood what I'm saying and you think there's some mistake in what I've said?
No, not at all, sir.
Okay. So let's go on. So it's clear to everybody that this is the initial object. Now about final object? Yeah? Somebody tell me final object. So final object, let's call that final object F. That's such an object that given any X, there exists a unique arrow to F. Unique continuous map. So what will you take F to be?
Sir, singleton.
Absolutely. Singleton space. Which we will often denote by this symbol. So which means it's a pair where X is a singleton set. Okay. So X is a singleton set. And what is T? T has the empty set in it and also the singleton set in it. This is X, which is a singleton set, and this is T. And now given any X, you send every X to this thing. Okay. As a set, it is a singleton set. So send every element X here to this same thing. Yeah. So what's the inverse image of this fellow under F? Inverse image of empty set is
Empty.
Empty, and it is open in X because X has a topology in it. So X means XT. Okay. And what's the inverse image of this singleton?
Capital X.
All of X, and that's also open. So you see, and there's no other map possible, right? Where will you send anything? To the only thing that there is. So anything has a unique continuous map to this. So we have singleton and as a topological space, and it is the final object. So yes and yes, that is the answers. Yeah, is this point clear to everybody? Again, this is completely elementary. Yeah, just meditate on it till you are comfortable with it. Till you are not comfortable with it, you need to meditate more. I cannot do your meditation for you. Your meditation cannot be done by my holding your hand. I cannot hold the hand of 40 students as they wrestle with these concepts. You have to do it by yourself. You have to spend enormous time on it. Yeah? Go for a walk. Don't talk with anybody. Go for a walk and meditate on these matters. That's the only way of understanding concepts. Okay. All right, so we have introduced initial and terminal objects. Now let's do something more. How about our friends product? So as I told you, product is actually a triple, x cross y, px, py. And we suppress this notation usually and call the product just this. And coproduct, which means there is an underlying set which has that same name, and there is some jx and there is some jy, which are going in opposite direction. So these are some of the most important concepts in topology, and Simmons actually has product. Product is there in all books. Yeah. So the product is made like this. Recipe for product. So you have to say a recipe for product. You can have your own recipe. You can have your own recipe. So long as it satisfies the universal property and which will make it unique up to a unique isomorphism. Okay, so what is the universal property? The universal property is this. X cross Y, this triple, P1, P2, I'll keep changing its names, Px, Py, P1, P2, whatever. These are continuous. This is a diagram in top, which means X cross Y, object in top. P1, P2, arrows in top. Such that given any other object in top, given any other topological space, and two continuous maps, arrows in top are called continuous maps. Given any f and g, there exists a unique arrow h. There exists a unique arrow h making this triangle commute. The same universal property of product. There is no difference. We talked about products in sets. We talked about products in groups. We talked of products in vector spaces. We talked of products in commutative rings. We talked of products in metric spaces and their existence or non-existence. And remember, in metric spaces, there was big problem. And we now talk of products in topological spaces. So what does your intuition tell you? That what should I take? So let me write X cross Y very painfully as a set with topology. Let me call that topology T. So as a set, what should I take? So the set is just the set of ordered pairs. Means the product in sets. Okay. So what set to take and what topology to put on it, with a topology T on it. So set, I just take X and Y. I mean, pairs X comma Y. And I define P1 X cross Y to X to send X comma Y to X. And P2 sends to Y. This is P1, this is P2. Clear what is the candidate I'm going to try for X cross Y? Just the product set. Now let me attempt to define T. Next, I want to define T. What is T? A set of subsets of X cross Y. A topology is a set of subsets of X cross Y. These are the open sets. So please go to this diagram. I want P1 and P2 are arrows in top, right? So these are continuous maps. So I'm going to ask you a question. Let U be a subset of X. What is P1 inverse U? Bolo. And the answer is P1 inverse U is nothing but U cross Y.
U cross Y.
Correct? Similarly, if I take V in Y, P2 inverse V is equal to X cross V. So if this is open, and this is open with respect to topology on X, and this is open with respect to topology on Y. And I want P1 and P2 to be continuous, which means I want these to be open, because these are the inverse images open. We want this to be open in X cross Y. And also we want this to be open in X cross Y, because it is the inverse image of V. So you understood that if we want these maps to be continuous, we are forced to have these open sets. And now the good news, that's it. So now I want to make a topology with these as open. I want a topology to make a topology for which U cross X, sorry, U cross Y, isn't it? Is open for all U open X, and X cross V is open for all V which are open in Y. I want this. So what if I say, okay, these are all? Perhaps this is already a topology. Will you think this is already a topology? What should a topology satisfy? Empty set. Is empty set of this form? Yeah, is empty set of the form U cross Y? Okay, empty set causes your wicket to be lost, is it? Bolo, is empty set of the form U cross Y? I have this empty subset in X cross Y, no?
So we can write empty cross empty.
But empty cross empty is not of this form. But you are on the right path. Just go take the next step.
Sir, we can write empty cross Y.
Correct. It is empty cross Y. It is also equal to X cross empty.
Yes.
So, okay, empty set is indeed of this form. So, empty set is there. One condition satisfied. How about all of X cross Y? Well, take U equal to all of X, or take V equal to all of Y, then U cross V is X cross Y. Is U cross Y for U equal to X? Also, it is equal to X cross V for V equal to Y. Okay, now what do I want? I want unions, arbitrary unions. How about Ui cross Y and I take the union of such? What is this union equal to? Suppose Ui is R open sets in X. So what is union of Ui's cross Y? Girls will answer quickly. See, now I slowly begin to understand why Simmons spends a whole chapter talking sets. Bolo.
You can take union inside.
Loudly, loudly.
Yeah, union inside. Union of Ui cross Y.
Correct. So it is the union of Ui cross Y. Or what is some other family Vj of open sets in X, and I take X cross Vj equal to, bolo,
X cross union Vj.
Yes. Okay. And if I have something of this kind, but then I might have union of both things. So now what I should allow is, if I have something from here, if I have Ui cross Y, and take its union with X cross V. You see, this looks like this. One of them looks like this. And let me change the color. The other one looks like this. Then their union is not of this kind, or their intersection is not of this kind. So what I should take is, the answer is now very obvious. What I need is union of something from here and something from there, or intersection of one thing from here and one thing from there. So what is the intersection? U cross Y intersection X cross V. What is this? This is equal to, look at the picture. What's the intersection? So this is like U and this is like V. Yeah, this is equal to U cross V, right?
U cross V.
So I want U cross V to be open. My motivation should come from R2. This is U cross V. So what I should do is take the smallest topology So what does smallest mean? Take the smallest topology. Smallest topology, I'll have to justify. T on X cross Y, for which all sets of the form U cross Y, where U open in X, and X cross V, where V open in Y, are in T. So what does smallest topology mean? Well, it means something very simple. If X is a set, so this exercise, if X is a set, and if Ti, I belonging to I, is a family of topologies on X, then intersection Ti is again a topology on X. That is the meaning of smallest topology. Why? Because I have family of open sets, okay, and it is open in each one of them, then the union is in each one of them. So the union is in the intersection of them. Same, I have finite family, and then the intersection is in each one of them. So the intersection is the intersection of them. So intersection means and that's all you have to remember. Okay. So this topology is smaller than all of these. So you take all possible topologies which have all these things and just intersect it, and that topology will therefore be contained in any other topology which has these properties. Or instead of being so one step abstract, you may want to describe what are the open sets, and for that the terminology is basis and sub-basis. So you say that sets of the form X cross V and U cross Y, sets of the form where U is open in X and V is open in Y, are a sub-basis for T, which means arbitrary unions, so let's call that collection B, or SB, this is a sub-basis, arbitrary unions of finite intersections of sets in SB are the open sets. So you see, the argument is pretty clear up to here. You have to allow these things and you have to allow these things. For this projection to be open, the inverse image of U is U cross Y. For the second projection to be open, the inverse image of V is X cross V. You want both these to be open. Now I want intersection of open sets to be open. So I am forced to allow finite intersections. And I want unions, all unions of open sets to be open. So I allow arbitrary unions. So I just take the sets of the kind which I am forced to take as open, and then just put in their arbitrary unions and finite intersections, because topology requires those also to be there. So just put in there, don't put in anything more. So you have done the minimal possible thing. You have just put in what you are forced to put in and not put in anything more. Okay, then that is the smallest topology. That's why it is smallest. You have only fulfilled the necessary conditions which have been imposed on you. You have fulfilled all the necessary conditions, and therefore that is sufficient. And you have not gone and done one extra thing. Yeah, understood? So now at this point, I want to ask you a question which will tell me how fast I should go. So you guys have, most of you have seen the definition of product space before this? Yes or no? Because the prerequisites of AFS-I said that the candidate should be familiar with the first 3 chapters of Simmons. Yeah? So have you guys seen the definition of topological spaces? Whatever I have said so far about topological spaces, forget the way I put it, but at least you know what's topology and what's product, what's continuous map. Yeah? Yes or no?
Yes, sir.
Is there anybody who does not know? Okay, so all of you know. So do you think I should speed up? Should I go faster next lecture?
No, sir.
No, but you already know all this. Because this, at this rate, I'm going to take a huge amount of time. Okay, so let me therefore ask you the next question. So now I have set up X cross Y, I have set up T, and you verify the universal property. What is meant by the universal property? This one. that now you have to verify that P1 and P2 are continuous. Yes, we put in exactly all those open sets which are required to make P1 and P2 continuous, and we put in all those extra open sets to satisfy the definition of topology. So P1 and P2 are continuous. Now given any V and two maps, you want to show that there exists H. So what would be the formula for H? Just tell me. Where will it send some small w? Yeah, it will go to where? FWGW. Where else can it go? Because this triangle has to commute. The small w this way goes to GW. Small w this way goes to FW. So water element here has one projection FW and one projection GW. So the element here has to be FWGW. So this W has to go to FWGW. That's the unique possibility. You only have to check that the map so defined is continuous. Okay. So check HW, define it to be equal to FWGW is continuous. That's pretty obvious. If I take any open set, what is its inverse image here? So let's call it F inverse U. Now, if I take its inverse image here, it is U cross Y. And I want to take the inverse image under H of U cross Y. And that will be F inverse U. So just set it. Okay, so I have still some time left. So now let's move to coproduct. Coproduct. So coproducts exist in top. Okay. But actually, you know, even arbitrary. So here we are talking of binary. But even arbitrary products exist in top. Arbitrary coproducts exist in top. Top is wonderful in those respects. It has all those things: arbitrary products, arbitrary coproducts. So so I want to manufacture X. Here's the recipe. I'm going to give you the recipe. The recipe is, as a set, take the disjoint union. So with that, once you take the disjoint union, this is X and this is Y. Just put them side by side, apart, so that they don't intersect. Put them far apart. That's called disjoint union. Now, how does a subset of X cross Y look? Let's write a subset in red, or this funny color. A subset will have some portion here and some portion here. Okay. So subset, let's call it Z of X disjoint union Y. Then Z is itself a disjoint union. Z1 union Z2, where Z1 is in X and Z2 is in Y. Okay. Now I define a topology. Declare Z to be open in X disjoint union Y if both Z1 X and Z2 Y are open, which means Z1 has to be open here and Z2 has to be open here. And that is defining for me a collection of special open subsets of X disjoint union Y. I declare them to be open. This is a topology. Check. And it has the universal property. What's the universal property? I have From X, I have map J 1 to X disjoint union Y, just put it in as it is. And from Y, I have map J2, just put it in as it is. So remember, in one construction, I could take this to be X cross 1 union Y cross 2. And in that case, J1 is going to send some point X to X comma 1. And it's going to send some point Y to Y comma 2. And now the initial property is given any other topological space W, sorry, I'm jumping the gun. Given any topological space W and given two continuous maps, one is F and one is G, there should exist a unique continuous map H making all this commute. So you have to check. So homework. 1, check X disjoint union Y is a topological space. Second point, J1, J2 are continuous. And the third point is this triple X disjoint union Y, J1, J2 has the universal property of a coproduct. This is the universal property of a coproduct. Okay, so I have run out of time and I am stopping.